So we are starting a very important topic, PDE solvers. So there are three types: parabolic, elliptic, and hyperbolic. So this PDE classification is critical. So parabolic, I'll give only examples. I will not do the math part of this. So d by dt, this partial t is Laplace in psi. Diffusion equation is parabolic. Okay, so these are linear equations. We can also make it non-linear, which I will do it later. Elliptic equation is example of elliptic equation. You've done this in your math course. So example of elliptic equation. Oh, what? No, wave is not elliptic. Wave is hyperbolic. Laplace's equation. So this is elliptic, and hyperbolic is psi. Okay. So we will do only these two classes, not this class. I will do one. Well, I will basically make a slight excursion into it, but I will do these two, not this. Okay, it's more complicated. Okay, so let's look at first this equation, how to solve it in 1D. So dt d psi is alpha d square psi dx. Okay, you know how to solve this? By what method? Separation of variable. Then what? So separation of variable will not really. Well, first who solved this equation? The first person who solved this equation. I tell you this in the last semester. So this was done by Fourier first. He does, well, it's not separation of variable, but Fourier 1817, and in fact the Fourier series he solved using Fourier series. Okay, so the idea is to expand. So we'll assume that I am solving in a 1D grid where psi is 0 at both the ends. Okay, let's assume that. So it's very similar to particle in a box or infinite potential. So psi equal to 0. So I can, if this is the case, then Fourier says, this person Fourier, he says that psi x can be expanded in terms of sine functions, sine kn of x, kn. Okay, I can expand in terms of Fourier series. So this is what he told first. Now this is a very important theorem. You can, using this function, using this expansion, you can expand any function, in fact even discontinuous ones. Okay, so if you, well, I'm sure this function can also be written in terms of this. So there is a discontinuity at this point and this point. So Fourier didn't know the proof, but he postulated that this can be done, and that's the reason why he was struggling. I mean, nobody believed that time. Yeah?
Why are you going with the discontinuity?
There is a discontinuity, no, here at this point there is a jump in the function. There is a discontinuous function. The derivative does not exist. It has two values at this point. Okay. So, but it's a very important expansion. Now, using this, let's try to solve it, this equation. So, what we do is we'll make, so this function of x and t. Now, x part I will, so one more point, kn is n pi by L. L is the box size. Okay. So this one I'll make a function of time, this coefficient. Okay, so x dependence and t dependence are separated out. So in some sense it is like separation of variable, but this way I am going to give the full solution. Now let's plug it in here. So what do I get? Sum of, so time derivative will act only on this. So d by dt of k and t. So right hand side will be minus alpha. So if I take the double derivative, what will I get? Kn squared psi tilde kn. Now I forgot, I had to put a sin knx here. Okay, so I can take it to the left hand side, and this gives us some. So written I can write like this, right? This is a notation. Psi n means here nth, so kn, so this index n. Actually, since we are going to use, okay, so we have to, okay, let me just put a k here, kn, okay, plus alpha kn squared psi head of kn sine. Now what can I say about this? What can I say about this? What? Should be 0, because these are independent basis functions. So if this to be 0 for all x implies that this quantity is 0. So hat is the Fourier transform. Okay, so I have converted my partial differential equation into ODEs. So they have become ordinary differential equation, and how many of them? Infinite of them. So n goes from 1 to infinity for this case. So infinite equations. So but I have succeeded in converting to PDEs, PDEs to ODEs. Now in practice we don't need infinite series. So how do I cut it off? So it is impossible to get infinite series, no, in practical life. So how do I cut this off? So there will be highest wavelength, highest wave number here. Okay, at some point it has to cut off. Right? There are fluctuations, but the fluctuation with highest wave number is up to that point only I need to go. So there will be, if I look at this time series, I will have something like this, then like this, like this. So there is a shortest wavelength, and shortest wavelength corresponds to min k max, which is L by k max 2 pi by lambda min. I need to only sum up to that point. I don't need to go beyond it. Okay, and given the time series, somebody gives you the function, I have to just do this, find the lowest wavelength. So this is a set of n ODEs, and I can now use my techniques to solve these ODEs. It turns out this linear equation it has exact solution. This was Fourier did. Fourier wasn't using a computer. So this has a solution. What is the solution for this? Kn is equal to psi n alpha k n square t. Now each of them has exact solution. So what is my final solution? This t. My final solution will be xt but I am not done yet because I need to find out what this is. So how do I compute this one? How will I compute this? This is t equal to 0. So this has to be computed from the initial condition. So I will give you the initial condition psi x equal to 0, psi x at t equal to 0. From this you compute, do the Fourier transform, and that will give you. Okay, so this solved. This is how Fourier solved it, and it has exact solution. But I want to do it numerically. Okay, this looks very simple equation, but let's do it numerically and figure out what are the issues for this problem, and it will help you also to solve other more complicated problems. Okay, so which method? So let's do the blindly simple method, which is Euler. So first let's do Euler method. Euler's explicit. This one. So this will be, so I have n of them, so for each of them I need to apply Euler. So psi tilde, I am going to put k. So that is why I was afraid of this. N will conflict with my time stepping n. So there is a the symbol, so I am just going to say this is k. For kn I am just specifying by k is a wave number. So n plus 1 equal to psi hat of k n. Now this is the right hand side, minus alpha k n squared psi k. By the way, this is spectral method, so some of you have chose spectral method. So this is using Fourier transform. So you can use this method to solve many differential equations, PDEs. So this is really the spectral. Spectral means I am breaking into different spectrum, that prism spectrum, that's what we do. So I have broken into different spectrum. So these are equations for different wave numbers or different colors of light, if you like. Okay, so we are solving this. So this will be 1 minus, no sorry I forgot, delta t, no? So it is a function of time. Now, so we have two things. One is I have discretized in time and I discretized in wave number. So I need to, so I start from t equal to 0, I go to t final, but let's assume that I have done uniform discretization in time. So this is delta t. So this must be delta t here, correct? Euler explicit scheme. Yes. So this is going to be minus k n square delta t psi hat of k n k. Now, yeah, this one. So given the initial condition, so this is my solution, but I need to compute this, right? Now this is my temperature in Fourier space at t equal to 0, and how do I compute it? How do I find it? So given the initial condition I can find that, right? So this is a initial value problem and solving this given the initial value. So initial value I have to give you what is psi x at t equal to 0. Okay, So once I know this, I can do the Fourier transform to get this at t equal to 0. You can do it wrong. I mean, should I write it or? So you have to do the inverse transform, and that will give you psi k, psi of this integral psi x sine something like this. Okay, there will be some factors 2 or something. So that's the inversion. Okay, now so this is my coming from Euler scheme. Okay, the problem will come. So if alpha positive for diffusion equation, things are fine. This will converge, or for alpha positive, this quantity is real. So my psi n plus 1 will decrease, like it decreases here. Now there can be a problem if my delta t is too large. So what can happen? If this quantity becomes minus 2, minus 1, as soon as this quantity becomes less than 0, then there is a problem. So I want this function to be positive if this is positive, but as soon as this becomes less than 0, then there is an oscillation, and the real solution does not have oscillation. This is monotonically decreasing, so this creates oscillations. And when does the oscillation starts? Alpha k n squared delta t greater than. So for my well behaved nature, so this is stability. For stability, so that means I do not want this oscillation. This is very similar to oscillations we were getting for unstable solution. It is supposed to monotonically go down to 0, but it's oscillating now. So for stability, I require that this condition should not happen. So I require that alpha k squared delta t must be less than 1. So delta t must be less than 1 by alpha k squared. Okay, this is critical. So when you do your project, you have to keep this in mind. Now what is Kn? So Kn is, I said, so look, for every Kn I have a delta t. So what is the worst delta t? The lowest delta t. So right, so every equation has a delta t correspondingly. So lowest delta t will be 1 by alpha k max squared. So what is k max? So that will be 1 by pi squared lambda min. Okay, now so I am going to go now to the finite difference. So this is so we can also estimate what is lambda min. So we have a grid. So now in real space, now just so far I was in Fourier space. These quantities are in Fourier space. But you look at the real space data. So this is x. So we got this is delta x. So this will be h. We call it h. Okay, real space separation is called h. Now what should be, so this is called Nyquist criterion, I will not describe that. So Nyquist criteria. So lambda, according to that lambda should be, so here the wavelength, so the lowest wavelength should cover 2h. So that's a Nyquist criteria. So lambda equal to 2h. Okay. So you are okay. So the criteria tells you physically that given the time series, if I want to resolve it using Fourier transforms, or I want to resolve it, not necessarily Fourier transform, even by finite difference scheme, so the lowest wavelength should contain 2 points, 2h. So suppose there is a signal coming from the radio station, I want to filter it, I want to analyze the time series. So what should be my spacing of delta x? So my delta x must be, so that is delta x, x must be lambda by 2, lambda mean by 2. Okay. So this gives you a relationship between delta mean and h. So my delta t, if I use this, I get, so lambda mean will be 4 squared alpha plus 1. Okay, so I am just substituting it here. So from this I am getting a clue what should be my delta t for my PDE for partial differential equation solver, and what should be my delta x. This is very critical for all the projects. You have to be very, very clear what should be my delta x and what should be my delta t. If you don't choose it, your code will blow up, it oscillate, it will misbehave, it won't work. Okay, and this is called CFL criteria. Okay, so I know what should be my delta x and what should be my delta t. Now this is how we solve diffusion equation in spectral method.